Hi, my name is Kevin Shu, and this summer I participated in the Summer Undergraduate Research Experience at the University of Michigan. I work with the Nuclear Engineering Department and Professor Thomas Downer on validation testing of nuclear reactor codes, PARCS, and MPACT. Nuclear reactors depend on a physical phenomenon known as nuclear fission. Fission occurs when a heavy unstable nuclide, such as uranium or plutonium, is split into two stable daughter nuclide. In the process, 2 or 3 neutrons are typically released, and these neutrons play an important role within the reactor. The reason we use fission is because of the incredible amount of energy that is released per fission. A typical fission has around 1,000,000 times the amount of energy as a conventional chemical reaction. Fission neutrons are important because they can cause other fissions within the reactor. The movement of neutrons is governed by the neutron transfer equation, which is the form of the Boltzmann equation. The population of neutrons within a reactor is described by the reactor criticality. We say a reactor is critical if each fission can cause a subsequent fission. There are 2 general approaches to solving the Boltzmann equation. Stochastic methods use probability and random processes to try to find a solution. Deterministic methods use numerical methods and variables that are largely determined by parameters to find a solution to the problem. One of the main codes I worked with was MPACT, the Michigan Parallel Characteristic Transport Code. MPACT is currently being developed at the University of Michigan and is designed to perform high-fidelity analysis of light water reactors. It uses a deterministic method known as the method of characteristics to perform core calculations. Some of the other codes I worked with include PARCS, MPACT, and CASMO. PARCS is a reactor core simulator that is used throughout the world and originally developed for analysis of light water reactors. MPACT performs cross-section generation. Cross-sections are essentially the probability of a nuclide undergoing a certain reaction. CASMO is a neutron transport code and is also capable of cross-section generation. Most of my work throughout the summer involved modeling and performing calculations and comparing the results to published data. Building the model in CASMO required many steps. I had to define the temperature, pressure, and other parameters in the reactor, define the materials present in the reactor, and specify the geometry of fuel pins, guide tubes, and other reactor elements. While constructing the reactor geometry, it was important that I first started with the smallest element, defining the individual fuel pin. I then moved on to defining the fuel assemblies and eventually the entire core layout. The problems I worked on throughout the summer were the AMA core benchmark problems provided by the CASTLE project. Completion of the benchmark problems assists software and method developers in progressing through capabilities needed to model a real reactor. Beginning at the pin level and working to the full core allows developers to see exactly which places need improvement. The chart below contains some of the results of problem 4, which was the 3D assembly cluster. The second column contains the calculated eigenvalues of our simulation model, which was built using PARCS and CASMO cross-sections. The third column contained the reference eigenvalues provided by CASTLE. The fourth column contained the PCM, or the percent mil, which is a method of calculating the precision of our simulation. We expected the PCM of the assembly cluster to be no more than a few hundred PCM, and from the results we see that the PCM are roughly in the range of 3 to 500, which is pretty accurate. This tells us that our simulation is matching pretty closely to what is actually happening within the reactor. The next step in the work would be to do problems 3 and 4 using MPACT generated cross-sections. This would allow us to directly compare MPACT and CASMO cross-sections and assess their accuracies. After that, we would move on to problem 5 3D using MPACT and CASMO generated cross-sections. The published results for this problem were taken from real plant data, so comparing our simulation results to these data would be a significant benchmark. I would like to say thank you to the members of the Nuclear Reactor Analysis and Methods Group at the University of Michigan, and a special thank you to Professor Thomas Downer, Dr. Andrew Ward, and Thomas Aller for your continued support and your help throughout the summer. Thank you.